Hello, everyone. So, first things first, I want to go over the test because just to reiterate, the final is cumulative. So these questions are very good examples of something that you might see on the final exam. Of course, you also need to know everything that we covered on the first exam, um, but I'll get to that a little bit later. So we can see uh, April 30th is when we have our final exam. So we have this lecture for today, and then we have 3 more weeks of lectures. Ideally, the last week at least, I would like to review. So that only leaves us at most 2.5 weeks of new material. So uh, these may be in a different order than you received them, but the first one we are given the following Weibull distribution, and this is an example of what kind of function. So immediately we should hopefully know that the Weibull distribution is a continuous distribution, so we can rule out a probability mass function, but of course we can also look at the support and see it's an interval, so again we can rule this. Now technically, without having prior experience looking at the Weibull distribution or looking it up, of course, I've basically hinted I wasn't trying to be tricky. I did put lowercase f, but just if this was all that was given to use this function to choose between these three, technically you could verify that it's a probability density function by integrating from 0 to infinity, and which case this would be 1, right? Area under the curve is 1, which would verify that it's a probability density function. Um, probably just recognized it though, or you could just simply look it up as being the density function or probability density function PDF for a Weibull distribution. Okay, so one thing, it looks like that the shape is 2 and the scale is 4, but notice right here we have 1/2, which hopefully didn't fool you, but of course that's just 2 divided by 4, but the shape is still 2 and the scale is 4. Scale is 4, shape is 2, 2 minus 1, right? Okay, so that's why it's a PDF. Recall CDF, of course, is capital F. It gives us less than or equal to probabilities, and in order to get this, it would be the integral of this from 0 to, say, y. Right? And of course, survival function gives us greater than probabilities, and it's just 1 minus the CDF. Okay, so for this one, we again have the exact same Weibull distribution. This time we're saying it's time till failure, and we want the probability that a part lasts at least 5 years, given that it lasts at least 3 years. So on one of the previous, I think number 1, exam 2 number 1, we have a pretty much exact same question right here. You know, probability that it's greater than 12, given that it's greater than 10, right? In this case, we just have 5 and 3. And so we use our basic probability rules to get here. Because we're talking about time, we've seen this a bunch of times, this simplifies into greater than the bigger number. And it looks like, say, the survival function evaluated at 5 divided by the survival function evaluated at 3, because those are the numbers that we have. And so in order to avoid doing two integrals, we can calculate the survival function. In this case, I calculate the CDF and then just take 1 minus the CDF. But this is a Weibull distribution, right? So immediately we should know u substitution, setting this exponent to u besides the minus sign. Take our du, make sure to change the bounds, right, which only affects the upper bound of the integral, right? And then this integral right here is extremely basic. So calculating that shouldn't be too difficult. And then now we have this. And so for this problem, it's the exact same problem. The only difference is we have 4 as our scale instead of 10. So everywhere you see a 10, replace it with 4, and then it's the exact same thing. So what we should get is the survival function is this, except 4 in the denominator here, t divided by 4. Okay. And so we just have this with 5 divided by 4, and then on the lower hand we just have 3 divided by 4. Okay, and that gives us our answer. So that should not have been very difficult to do if you did it this way. However, there is a way to simply do it in R. Okay, so where are we? We are here. So again, we know we have this Weibull distribution. We know its shape and we know its scale, right? We know its parameters. And again, this is asking, or we determine we can simply look at this as the probability that it's greater than 5 divided by probability that it's greater than 3, right? Because those are the numbers in our case. Well, we can calculate probabilities for a Weibull distribution in R, right? And that's P Weibull. So 5, 2, 4, right? The probability of being less than this, shape, scale. Okay, but of course we don't want less than, right? We want greater than. So in order to get that, of course, we just have to subtract it from 1, right? So that gives us the probability that it's greater than 5, the Weibull distribution with shape, scale, and then divided by the probability that it's greater than 3. And bam, that's actually all you had to do. Okay, so either way should not have been too awfully difficult, and we can see that that is option number 1. Okay, if you did it an incorrect way, I tried to put a few choices that you could have gotten if you did it some incorrect way. Okay, same distribution. Now we're trying to determine if part gets stronger, weaker over time. And our go-to thing for that should be the hazard function. Okay, of course, there is a trick for this because it's a Weibull distribution, but I don't always have to give you a hazard function question like this for a Weibull distribution. Okay, so I will go over again how you do it in general, but for a Weibull distribution, we know if the shape is greater than 1, then the hazard function is increasing, and thus the part is getting weaker. Okay. If the shape had been less than 1, the hazard function would be decreasing and it would be getting stronger. If the shape was equal to 1, okay, equal to 1, then it would be constant. And of course, this is just a filler. Okay, but in general, it's very similar to this. So calculating the hazard function is the PDF divided by the survival function. And so for Weibull, it would look like this. Of course, just replace those 10s with 4s for our current example. And so to determine whether it's getting stronger or weaker, we need the derivative of the hazard function. So taking the derivative of this, we just get 2 divided by 4 times 4, right, in our example. So 2 divided by 16. And of course, that is positive always. Thus, the hazard function is increasing. And so it is becoming weaker, more likely to fail. Okay. And if it was negative, it would be decreasing, less likely to fail. And if this was, if it was 0, the derivative was 0, then it would be constant. Okay, so we're modeling some bridge cable data, time until they need to be replaced. We have 100 observations, and we're trying to determine whether a Weibull, normal, or exponential model seems most appropriate. So after we download the data from Blackboard, put it on our desktop, okay, exam2 bridge, go to our Weibull analysis code so that we have to modify as little as possible. Exam2 bridge, remember everything is case sensitive and space sensitive and everything like that, so we have to put everything exactly. Pretty sure it was this lecture that got deleted. Someone was telling me that on Macs, I know things are a little bit different on Macs. Apparently this double backspace doesn't work, but this single forward, or slash rather, this single forward slash works, and I believe this actually works on Windows as well. So maybe I should just update the code to single forward slash so it works for everybody. So my data, my 100 lifetimes, time to failures of a bridge cable. And so the first model we want to fit was a Weeble, and so we don't need that. So ignore this warning messages. Oops, I killed the comma there. Have to put that back in. Right, put our shape and our scale. We still have Weeble. Copy paste that. Let's see what the QQ plot looks like. Got to click back over here. So this doesn't look. This isn't actually amazing, but it's not bad. We do clearly have one kind of outlier. The one thing, right? These are all kind of close to the line, but the one thing I don't like is just how, even though they're close, they're kind of all on this side and then kind of all on this side. If you look closely, you can kind of see that. So that's not ideal, right? But they're clearly not straying away from the line very much. So this looks decent. This looks decent, except one noticeable outlier that the model doesn't seem to hit very well. Okay, so not perfect, but not bad. Histogram. See what the histogram looks like. Got to put our parameters in, or our estimates rather. Maximum likelihood estimates, right? That's what these are. That's what this fit_dist_r function gives us, is maximum likelihood estimates, because we're maximizing a likelihood. So, right, this is a hump. It just gets cut off because the graph ends here. But this is a hump, and so it starts at 0, right? We're talking about lifetimes. That's good. It goes up, kind of humps right in the middle of these two, or a little closer to that. That looks good, and then goes back down. So that looks very good. So right now, it's looking like a Weeble distribution is a very good contender. Okay. To save a little bit of time, I'm just, for this normal distribution, going to jump right. I wonder if I can copy both. I'm going to jump right into the histogram. Okay. Don't forget to change our distribution as well as the parameters. Okay, and so the reason I'm just going to skip right to this is because this has a horrible flaw, right? This doesn't look awful, right? The hump is clearly further to the right, it looks like, than we want, but what's awful is this right here, right? This symmetric distribution, so this tail continues on, and this is quite a bit of probability that's being assigned to negative values. We're talking about time. So this normal distribution is just absolutely horrible. And if I were to look at this first, there's basically no need to even go look at the QQ plot, because I can immediately rule this normal distribution out based on this histogram. Okay. So now I just click up exponential. Okay, single parameter. Don't forget. See what this QQ plot looks like. Clearly inferior to the Weeble distribution, right? The lines are much further away from the line, and we still have that pattern of they're kind of all on one side or the other for long periods of time, but they stray much further away from the line. Okay, so this is clearly worse, but I guess just to verify, we'll go ahead and look at the histogram. Don't forget to change our distribution. It's going to not give us the right result. And so this is the histogram. So right, this just keeps going up, assigning the most probability to 0. And a little hard to tell, but it looks like the highest bar anyway is here. So it looks like maybe, right, it goes up a little bit and then back down. It doesn't look like it's highest at 0. So certainly both of these graphs, maybe especially the QQ plot, indicate that this is also inferior to the Weeble distribution, and that the Weeble distribution is clearly the best of these 3 available models. That we weren't asked about a gamma distribution. The Weeble is certainly the best. I didn't want to put any additional questions on this problem just for time. I wanted to make sure you had plenty of time to finish everything. But some follow-up questions if I were to put something similar to this on the exam is you now have a model for the data, right? You have a Weibull distribution with shape, right, and scale. Shape about 1.6 and scale about 0.45, okay? And so now when you're collaborating with other professionals, you know, you have this model that can be used to calculate probabilities and quantiles for when a bridge cable needs to be replaced. So for example, one thing that might be interest is the median amount of time until a bridge cable needs to be replaced. And we can easily figure something like that out, right? Q Weibull, median amount of time, that's the 50th percentile, right? 0.5 quantile, and we have shape and scale from our maximum likelihood estimates. And bam. So 0.36, assume we're talking about years, is the median amount of time until a bridge cable needs to be replaced. Another realistic scenario is maybe at the beginning of the year, you were in charge of not only the bridge, but other things throughout the city, and you are helping to determine where budget needs to be used. Does it need to be, do we need to allocate money to the bridge or some other project? Okay, so one thing that you could think about calculating is, okay, what's the probability that a bridge cable needs to be replaced before the first year or within the next year? And we can calculate something like that, right? P Weibull, 1, right? The probability that the Weibull distribution is less than 1, which the time until a bridge cable needs to be replaced, less than 1. And that's 97% chance, right? So there's a very, very high chance that a bridge cable needs to be replaced before the first year. So in that budget meeting, it's probably likely that you would suggest that you do in fact need to allocate some of the budget to replacing a bridge cable, right? So something like that is a very good follow-up question, and also a very basic but an example of how you might actually use one of these models that you construct for a data set to answer a real-life question. Okay, we're trying to see if Trump wins the next election. We take a preliminary poll of 1,000 people, 535 say they're going to vote for Trump. And so we want a 98% confidence interval for the proportion of people that are going to vote for Trump. And of course, we want to use that to determine if we have evidence that Trump is going to win the next election or not. Okay, so it's a confidence interval for a proportion. So proportion, prop, dot test, very easy. We have 535 successes, right? People that are going to vote for Trump, success out of 1,000 observations, people surveyed. And we can't forget conf.level equals 98, right? 0.98. We wanted a 98% confidence interval. And so this is our confidence interval. And if we look, this is exactly what's here, right? Notice these are very similar. Well, they're pretty similar, but they're not the same. Okay, this is what you would have gotten if you did a 95% confidence interval, if you forgot to put this. And in this case, it actually gives you the wrong decision. So this is the right confidence interval, and so we need the right conclusion. We do not have evidence that Trump is going to win the election. Okay, why? Of course, this is just simply based on him winning, or just dumbing it down to he receives more than 50% of the votes, right? Okay, kind of ignore the electoral college thing. And so we can see that 50% is within this confidence interval. So we do not have evidence that it differs from 50%. Okay, and of course that this is the opposite decision and the wrong decision. Now, if you had done the wrong confidence level, you would have gotten this. And in which case, this confidence interval would be properly interpreted as we do have evidence that he's going to win, right? Because the entire confidence interval is above 50%. However, this is the wrong way to do it, right? The wrong confidence level. So this is the right answer. And so notice when we went from a 95% confidence interval to a 98% confidence interval, we actually kind of flip-flop decisions. Here, at the 95% confidence level, we actually had enough evidence to say he was going to win, but at the 98% confidence level, we did not. Okay, so the more confident you want to be, you are going to require more and more evidence to be confident. Okay, right? And we would require even more evidence to be, say, 99% confident or 99.9% confident, right? But if we were only 90% confident, we would require much less evidence. Okay, so it depending on the problem, right? That's why in general, although 95% confidence is basically standard, depending on what you're talking about, right, and the severity of making a wrong decision, it makes sense in certain applications to have confidence intervals that are either less or more than 95% confidence. But that's kind of neither here nor there for this class. The next one, we have two facilities and we want to get parts from one of these facilities. So we need to determine which manufacturer, which facility to get our parts from. And we have 10,000 observations from each facility. Okay, and before we go any further, we can see this exam2 length data, which I have already put on my desktop along with the other data files. And we're not doing Webull analysis anymore, so I'm going to go ahead and actually label this, because in general it's a bad idea to just call your data sets data, because then you don't even know what you're talking about. So we can see we have 10,000 observations from facility 1 and facility 2. One thing, if you notice, if you try to scroll up, you can't even get to the top. There's too many observations. One thing that you can do, a little trick, if you put length, because that's our data set, bracket 1 comma bracket, okay, this wants to show you the first row. Because it is before the comma, it means a row. Usually what we use when we're doing analysis a lot of times is we put the 1 behind the comma to indicate that we would like the first column. But I'm just doing this so that you can see what the labels at the top are. Of course, you could just look at the Excel file and see that though. Okay, but you can see they're labeled A and B. So let's go. Now we have our data set. We can kind of see what it looks like. So let's go back to see what we actually want to answer. Okay, each data point is the error length of a product, okay? And so what do I mean by that? It's the difference between the desired length and the produced length, okay? And so provide a 95% confidence interval for the difference between the average error length of facility A and the average error length for facility B, and we want to use it to determine which facility we should get our parts from. So hopefully, right, we should be, from this sentence, be able to determine that we are doing a confidence interval for the difference between two means, okay? And so the next step is to determine which of the three methods. Recall, we don't have to do this by hand, but there are still three methods, and we have to tell R which of the three methods needs to be used. So there is no correspondence or matching between facility A and facility B, right? It's just an independent sample from facility A, independent sample from facility B, so we can rule out that matched pairs design method 3. So to determine which of the two independent samples that we need to determine whether the variances are equal or not. Okay, so one thing we can do is a box plot. Okay, recall this is what's usually more useful, right? This is from the facility A, this is from facility B. So this tells it bracket comma 1 bracket says the first column of this linked data set. And likewise this, putting a 2, says the second column. Okay, so now we have side-by-side box plots, and we can see that these look pretty darn similar, right? Again, this being shifted up a little bit over this one has absolutely no bearing. We're just looking at the spread across the y-axis. And overall, these look pretty darn similar. Another thing that we could do is we could just look at the variance of each one. Length 1, variance is that, length 2. So we've got about 0.97 versus 1. Okay, those are pretty darn close, especially with the large sample size and these being close. I would probably be comfortable using the one where they have equal variances, okay? But in this case, actually, it doesn't matter whether you tell it to use equal variances or not, because they're so similar and because the sample size is so large, whether you say equal variance or not, it's actually going to give you the exact same answer to many, many decimal places. But in either way, t.test, and of course for some of these tests, right, I should have sent you a code. I believe it was this. Hopefully that didn't just screw everything up. I sent you this, and I sent you this, and it has quite a few of the intervals for you, okay? And so we can see we have two samples, equal variance, so we need to use this t.test function. So t.test length 1, length 2, right? Group 1, group 2, and they're in our combined data set like that, so that's how we need to put it. Var dot equal equals true. So two sample t-test, and this is the answer that we get. And it is exactly, oh, there it is. Yep. It's exactly this one, right? So it's this one. Notice that this one is extremely similar, right? You actually get the same answer if you do it this way. However, this is what the output looks like if you put paired is equal to true, if you do the matched pairs, which is not the right way to do it, and in many cases could actually give you a different decision. So this is not the right way to do it. We have to use this confidence interval. And of course, this confidence interval is completely negative, right? So we have evidence. And so, but it says we have evidence that facility A should be chosen. So this is a problem where I think it takes a little bit more time. You have to really read into what you're talking about. Okay, so each data point is error length, right? Error length is bad. So we have evidence, because this confidence interval is completely negative, we have evidence that the mean for group 2 is bigger, right? Something minus something is completely negative. Group 2 is bigger. And so that means the average error length for facility B, group 2, is bigger, which is bad. And thus we have evidence that facility A has a smaller average error length, and of course, that's why we should choose it. All right. Hypothesis test. We want to do a hypothesis test at the 0.05 level of significance to determine if we have evidence of a difference in the average lifetimes among three types of batteries. Okay, let's get our data. And in this case, battery, and I think it was actually lowercase, which we have to put away. Oops, I'll go ahead and change this to, I'll just call it bat. Let's see what this looks like. Okay, so we have 90 observations. We can see this 30 is from battery 3, this 30 is from battery 2, and this 30 is from battery 1, right? And we have the lifetimes here and the battery types here. So this is an ANOVA problem, and we need this line. And of course, species, if you recall in that example, one thing we have to do first to make this easier, make our lives easier, is attach bat, okay? Attaching it allows us to type these things in and be able to use these. If you don't put attach bat, you actually have to kind of do what we did before, is like bat bracket comma 1, bat bracket comma 2, okay? Okay, so species is like our battery type, our second column label, and this was our variable of interest, which was lifetime, right? That's the label for the first column. And so our p-value, right, is 2.2 times 10 to the negative 16th, which is just basically 0, right? So of course, just to kind of reemphasize here, right, the null is that the means, right, the mean lifetimes are equal, right, for the three types of batteries. The null, or sorry, the alternative is that, right, they're not, right? At least one type of battery has a different mean lifetime. And so we have a p-value, right, a very, very small p-value that is less than alpha, right, the significance level. So well, it's basically written here. So the p-value, right, 2.2 times 10 to the negative 16th is less than alpha, 0.05, the significance level. So we reject the null hypothesis that the average lifetimes are the same, and so we have evidence that the average lifetimes are different. Okay, this one says fail to reject, right? So that's the wrong decision. And going down here, this says we reject the null hypothesis, which is right, but it says that we don't have evidence, right? So this is why this one's wrong, and of course those say fail to reject. So that's the conclusion that we come to for this hypothesis test. The next question is, again, the same problem, but it says, do we need to do Tukey pairwise comparisons? Okay, and of course, Tukey, that is where if we find a difference in the means, right, we reject the null hypothesis and have evidence that they're different, which we do, that's when we need to do Tukey. So of course, this says we don't need to do it, so we can immediately rule that out. The others say that we do. And so we need to do Tukey pairwise comparisons. Oops. Which is here. And making sure to change our variables here. This was battery, and this was lifetime. Okay, always forget this. The fact that these are numerical, it doesn't like that, so we have to put as dot factor. If you notice this non-factors, it's kind of a hint. And don't forget to close your parentheses. And the error is gone. And so we have 3 confidence intervals, right? Each one of these confidence intervals is a confidence interval for the difference in the mean lifetime of battery 2 minus battery 1, right? Battery 3 minus battery 1, battery 3 minus battery 2, right? So just like the confidence interval that we just did in the last problem, these are 3 confidence intervals. And of course, it's 95% pairwise, right? So we're kind of 95% confident in the decision of all of these together. So anyway, to determine what we have, the confidence interval for 2 minus 1 is completely positive. Positive, positive. Again, ignore lower upper is all we care about. So we have evidence that the mean for group 2, is greater than 1. Looking at 3 minus 1, positive, positive. We have evidence that 3 is greater than 1. 3 minus 2, positive, positive. We have evidence that 3 is greater than 2, right? Thus, right, 3 is greater than both 1 and 2. So 3 has, right, battery 3 has the greatest mean lifetime. 2 is greater than 1, okay? Followed by battery 2, and then, right, 1 is less than 2 and 3, and battery 1 has the shortest lifetime. Okay, so we can actually perfectly order all 3 because all of the confidence intervals do not include 0. Remember, when one of them does, we're going to kind of have a question mark over here, and so we can't determine the ordering of all of them. We still might be able to determine the biggest or the smallest, for example, but we wouldn't be able to order all of them. But we can in this case. And so looking at it, this is what this says. Battery 3 has the longest, second, battery 2 second, and battery 1 shortest. Okay, so that is the test review, and I'm going to go ahead and split this into 2 lectures and hope that my audio did not cut out again for this one. Okay, so I don't have to redo it.